Hi everyone. This screencast is going to go over the equilibrium practice test. As you're working and going through the answers, please make sure you take some time to write down some of the tips and hints that I'm going to mention and that might be noted on the practice test. It may also be a good time to have your one pager out so that you can add some notes to that as well. All right, in the beginning here, we're going to look at things that must be true about a reaction at equilibrium. The most important thing to remember is that the rate of the forward and the reverse reaction is going to be the same at equilibrium. That's the equal part. Notice in the question it says what must be true. So if you are leaning towards C, this is possible that they could be the same at equilibrium, but it's not a requirement. Remember, you can have reactants being favored or products being favored at equilibrium. You don't have to have the same concentration of something, but what has to happen is that those concentrations need to become constant. Now for questions 2 and 3, I really want you to pay attention to the differences between what is being asked to be graphed. In question 2, you're graphing rate, and in question 3, you're graphing concentration. So with any kind of graph, please make sure you're paying attention to the axes labels, and that if you're asked to create a graph, you label the lines appropriately. Either forward and reverse, as we're seeing here in number 2, or in number 3, we're labeling the lines as reactants and products. So most importantly, remember when the rate must become equal at equilibrium. In question 3, we have a situation where the reactants are being favored at equilibrium. They have a greater concentration. But the idea that the concentrations of the reactants and products stop changing is important, and we can see that here during this flat part of the section of the graph. All right, now question 4, read carefully. You're answering each of the following that is true. So a couple of things that I noticed before I even look at the options. I notice that the forward reaction is endothermic because the heat is on the reactant side. I notice that the K is greater than 1, which tells me that the products are favored. I notice that I also have gases, so changes in pressure could cause a shift because I have different moles of gas on each side of my balanced equation. Remember, the only thing that changes the value of the equilibrium constant is temperature. Now, number 5 is an interesting question because you really need to think about the stoichiometry for this reaction. Even though we can't make predictions across the double-headed arrow, we still have to remember that on the reactant side, you have, according to the stoichiometry, you're going to need twice as much SO2 as O2. So this ratio here of 2 to 1 is still going to be true, and that's going to help us with our answer. So if we add 0.1 moles of each of these reactants to the reaction vessel, and then we allow them to reach equilibrium, we have to recognize that we're consuming the SO2 twice as fast as the oxygen. So that stoichiometry piece is tied to the rate, which you should remember from kinetics. So this means at equilibrium, even though you started with the same amount of your reactant, you're consuming the SO2 twice as fast, which is why you know you're going to have less SO2 compared to that O2. That's really the big understanding here. Now, number 6, this one is something that involves math, but it doesn't involve math. So it's a way that the College Board is going to get you to do some math without actual numbers. And they need you to think about which equation is going to represent the moles of ammonia that would be at equilibrium. And the easiest way to think about this is to use an ice diagram. So let's take a look at the ice diagram. All right, so in the ice diagram, I have color-coded. The blue is what was given in the problem. So in the problem, you're given the initial amounts of your reactants, and you're given the fact that you have Y moles of water present at equilibrium. So this means if Y is here, we have to follow our stoichiometry to get our change line. So we have Y, we have a third of Y because it's 2 out of 6. Here is 3 out of 6, so it's a half. And notice we're going from using up reactants here with a negative sign and then adding over here, which is the positive. And over here, I just simplified this 2/3. It was 4/6. I simplified to 2/3. So in order to find the amount at equilibrium, you would algebraically take the 0.3 and subtract the 2/3 of whatever Y happens to be. Number 7 uses an ice diagram as well. This one's not as challenging because you don't have any variables in there. But remember, think about your amounts that are given in your problem. Think about that hint. There always has to be some kind of hint about something that's at equilibrium or something that changes. And once you have that clue, you're able to fill in the rest of your ice diagram. So hopefully this is allowing you to see that little ice diagrams could also be important in the multiple choice. Now in number 8, the problem seems very similar to those that we've previously seen, except in this situation, there's no clue, there's no hint. They just tell you how much of something you started with, but they don't tell you what percentage decomposes or anything else. So there's no way for you to know what's present at equilibrium. There's just not enough information given. Number 9, similar to the ones that we've seen before, you can use an ice diagram because again, our clue for number 9 is at equilibrium, it is determined that 1.5 moles of ammonia had formed. So you can see again in the ice diagram, the blue represents all of the givens from the problem. Based upon those givens, we can fill in our change line here for that ammonia. And then that allows us to quickly and easily see the 2-to-1 ratio will allow us to know how much oxygen is present. I did fill in the rest of the ice diagram for you just so you could see how it works. But obviously, if it was a multiple choice question like this, you wouldn't want to spend the time filling in the whole thing when you only needed to know the amount of oxygen. All right, number 10. This question is showing you 2 different scenarios where you have one temperature at 25 degrees Celsius, you have a mole of your reactant, and then you have your equilibrium mixture, and it gives you the moles at equilibrium, and then you change the temperature. So the big understanding here is that changing the temperature is going to shift the equilibrium. So you really need to figure out when you compare your amount of products, the amount of products goes up when you are heating up your sample because it goes from the 0.37 to 1.0. So if the amount of product is increasing, it means that the K would also be increasing. So what can we conclude? The equilibrium constant will increase with temperature because, again, it's a ratio of product over reactant. Number 11, a little bit of KSP. One of the things that I want you to recognize for this is, one, you could have used a calculator because this would be, for some of us, a little bit tricky to use without a calculator. Although if you're on top of your exponent rules, you should be fine because you know that 4 squared is 16, and you're going to get a 16 here, and then you're going to get your exponent, and then when you again multiply these two together, you're going to get your 32, which gets simplified to 3.2. Your 12, your exponent here ends up being a negative 12, and then you have a negative 6, and then once you move all your decimals over, you could do this without a calculator. But watch out for the fact that you have to double your concentration of the hydroxide because it's 2, and you have to square it. Reaction quotient. Remember, this means you're not sure if the reaction is at equilibrium or not. So if you find an equilibrium mixture, or you're given some information about an equilibrium mixture and you're not sure if it's at equilibrium, that's when you calculate the Q. It's still products over reactants. Once you have the value for Q, you can compare it to K. So that's what we're asking you to do here in 13. The K is much, much smaller than the Q. So first thing we know is it's not at equilibrium because they're not the same. Since the K is much smaller, it means your Q value has to go down before it reaches equilibrium, which means you're going to need more reactants. The reaction has to be shifting to the left, back towards the reactants, in order for it to reach equilibrium. So that's what we need to figure out here. As it's reaching equilibrium, again, reactants should be going up in order to bring the value of Q down. So it will equal K. And there's a nice explanation for you also. We've got some more ice diagrams here for number 14. Again, the blue represents the given from the problem. You really need to remember here that you have to convert everything to molarity. Everything in the problem is moles. They give you the volume of the container. There's your clue here that you're going to have to take all of these mole numbers on the equilibrium line and divide by 2. Once you have everything in molarity, which is moles per liter, you can plug it into your equilibrium expression and then solve for the K. K is less than 1, so this tells us that the reactants must be favored. In a little bit of a twist for 15, you're given the K and you're asked to solve for an unknown concentration. So algebraically, you're setting up your unknown as x squared. Remember, the 2 coefficient here tells us it's squared. So just be careful when you're doing your calculations that you don't drop your cube, which is here. That comes from our coefficient there. Taking your time and making sure that everything is labeled will be really important when you're going through these problems. Now we're getting to some questions about Le Chatelier. The big idea from Le Chatelier, which I know is back here in 16, is that when a system is at equilibrium and it is subjected to a stress of temperature, pressure, or concentration, it will respond to counteract that stress and reestablish a new equilibrium. Remember, temperature, pressure, and concentration will cause a shift. Catalysts never cause a shift. And of the temperature, pressure, and concentration shifts, only temperature changes the value of the equilibrium constant. Number 18 is about temperature. Remember, when the temperature is decreased, the reaction wants to release some energy to warm that reaction system back up. So that means it will shift exothermically. 19, if the concentration of a product is decreased, we remove some product, the reaction is going to shift to make more product. So it shifts towards the right to bring that concentration of product back up. 20 is about pressure. Again, these are really straightforward, basic understandings. Pressure. If the pressure increases, the reaction shifts to try to decrease the pressure, and that means it has to shift to the side with fewer moles of gas. All right, let's skip on to 22 because this one's a little bit trickier. Again, be careful because it says which one or more of the following could be true. I notice here that the forward reaction is endothermic. That tells me something. I notice I have gases, so pressure is an option to cause a shift. I have 4 moles of gas on this side, 0 moles of gas on this side, so that could work. Liquids here, we can't change the concentration of a liquid, so nothing regarding these two substances would cause a shift. So be careful. Liquids and solids do not cause shifts. So this is why A can't be true, because it's a liquid. We could, actually, what are we trying to do? We're trying to increase, blah, 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 number of moles of this. Okay, so we're trying to get more product. So what can we do to get more product? Always read the question carefully. So we could remove some of the chlorine. If we remove the chlorine, that's going to shift the reaction to make more, which is also going to get more of our product of CS2. If we increase the size of the reaction vessel, the pressure drops. Remember, pressure volume inverse. So if the pressure drops, the reaction has to shift to the side with more moles of gas, which is what we have right here. And then we said previously the reaction is endothermic. So that means the heat is on the reactant side. So if the heat is on the reactant side, if we increase the temperature, that would be like adding more reactant, it's going to shift to make more product. So one of the things that you can remember to do is, like I said before, always add in that word heat in your balanced equation. There we go. We see it here. We see it as endothermic. Take a second, add the word heat in. So now you know I'm treating heat just like a reactant. If I added more reactant, I'm going to make more product. '23 is about pressure changes. We mentioned earlier you have to have gases, which we clearly do in all of these reactions. But the other thing to remember is the moles of gas must be different on each side of the double-headed arrow in order to cause a pressure shift. And that's why 3 isn't going to work, because there's 2 moles of each gas present on each side. '24 brings in some delta G information. Remember, when delta G is positive, the forward reaction is not favored. So that would also signify to us that the value of K is going to be less than 1. Because the products are not favored, the reactants are going to be favored because the forward direction is not thermodynamically favored. So making sure you remember how the sign of G can tell you the magnitude of K is an important conceptual information. So that means we know the KSP has to be very small. Forward is not thermodynamically favored because that would have to be a negative delta G. Remember, when you're given the delta G for a reaction or the K for the reaction or anything about the reaction, entropy, enthalpy, it's always for the forward direction. Magnesium fluoride very soluble? No, because we already said that the reactants are going to be favored and the reactants are in the solid state. The soluble form is the product state. Entropy is increasing. Yes, this goes back to the thermodynamics unit. Solid goes to aqueous. Number 25 is about a graph. What happened at time X? So the key thing that we're understanding is at time X, we get more CO and we get more Br2. So we're getting more reactants at time X, and our COBr here goes down. So what could potentially cause that? We also know our forward reaction is endothermic. All right, so decrease in pressure causes a shift to the side with more moles of gas, and that's what we're getting. We're getting more moles of gas here, so that's why it's going to end up shifting to the left, and we're going to get that to go up. If we increase the temperature, we'd be getting more of our COBr, and that can't work. And remember, adding a catalyst never causes a shift. Hopefully things are going so well so far. This next section, we're going to get into a little bit more of the Le Chatelier questions. This is actually the same reaction that we had on our Le Chatelier introductory worksheet. So it's going to remind us that when we change concentration, we can change the concentration by causing the concentration to go up. And that's what we're really seeing in 26. Adding iron chloride increases the concentration of iron, causes a shift to the product side. It's going to become red. But we can also decrease concentration by adding something to the reaction system that will essentially remove some of the reactant or product. It's going to remove something. And typically this happens with solutions. We remove an ion that's in solution by causing it to form a precipitate. So the clue here is I'm telling you that the iron hydroxide is insoluble in water. I could also tell you the KSP of the iron hydroxide is very small. That could be a clue, another way that I could give you this information. Because remember, KSP tells us how soluble something is. So you may not be told straight out, this is insoluble. The clue could also be that this KSP value is very small. Okay, so just keep that in mind. And again, if we remove then some of our iron, which is our reactant, the reaction is going to shift towards that side, which is going to be the side that's clear. All right, we have a couple interesting situations here in 28 and 29. A chemist combines reactants and observes a chemical reaction that is known to be reversible in the Kc to be 1.4 times 10 to the negative second, which tells us that the reactants are favored. The reaction occurs slowly and then appears to stop. How can the chemist determine if the mixture has reached an equilibrium state? Well, at this point, the best thing would be to gather the information that they have, the concentration values at that point, calculate the Q, and compare it to the K. Remember, if you're not sure if it's at equilibrium, the best thing you can do to test that out is calculate a Q and compare it to the K. Now in 29, the chemist is given amounts of reactants and observes a chemical reaction. It is not known if the reaction goes to completion or equilibrium. The reaction occurs very quickly, and then all measurable changes stop. So that could mean that it just reached its equilibrium. How can the chemist determine if the mixture has reached equilibrium or if the reaction has gone to completion. So a couple options here. You could try to calculate a theoretical yield and compare it to the actual yield. Then once you compare those two values, if it's gone to completion, your theoretical yield should be pretty close, or I should say your actual yield should be pretty close to your theoretical yield if it went to completion, because it means you made all your product. And remember, if a reaction goes to completion, you would make all product and consume all reactant. Something else you could do is you could try to test for the presence of a reactant, because if you had a reactant that's present, that could be an indication that you had something that's at equilibrium. So you're looking for the presence of both reactants. If there was only one reactant present, that could be the reactant that was in excess, which means it could be a sign that it could go to completion. So this one's, it's definitely caused you to think about all the different situations that could come up. So if you're given a question like this, try to think about what's different between completion versus equilibrium. Equilibrium, you have to have some amount of everything. In completion, you would have only products and maybe an excess of some kind of reactant. We're almost done. We've got about 10 to go. All right, so formulas and math. There's math on this, but definitely not as much as our thermo test. When you're going on to the AP formula page, obviously the section under equilibrium is where you want to look. You'll be focusing on the equations for Kc and Kp, but some other formulas that should come into play. PV equals nRT. Make sure the R that you're using here is, I listed the R that I use all the time, the 0.0821, or actually 0.08206. Remember, there's the one that's in torr as well that you could use, but it has pressure in it. But when you're using your Gibbs free energy relating to K formula, make sure you use the R that has the energy units in it, which is that 8.31. All right, 31. Again, we're trying to determine the extent to which the reaction will occur. You have to always think about there's kinetic things that are happening. A reaction could be reversible. There's thermodynamics that could be happening. This idea about reversibility means it could be in equilibrium. If a reaction has a negative delta G but doesn't occur, what could be the reason? Well, if it has a negative delta G, it means that it's thermodynamically favored, but one of the issues could be it could have a really, really, really high activation energy. And that could be a problem for why the reaction isn't really happening. The temperature maybe isn't high enough. Maybe it has a delta G, but it's being hindered by, it's going to be delta G negative, but it's only going to be at high temperatures, okay? So remember, that would be a situation where the entropy is favorable, but the enthalpy is not favorable, right? The reaction's endothermic, but the entropy is going up. That would only happen if you have a high temperature. And from a kinetic standpoint, that would be related to its activation energy. Now, let's say the reaction has a positive delta H, but it still happens really quickly. This kind of goes back to what I just said. Even though the delta H is positive, it could be the entropy that's driving the reaction. So this is a situation where entropy is driving the reaction, the temperature is high enough, it's able to happen very quickly. So you're noticing in question 31, we're really trying to get you to think back to other units that we've looked at and how all these units are going to kind of fit together. And that's what we really need to start thinking about now as we're getting closer and closer to that AP test, how does all the information from all of our different units go together? All right, let's see, 32. The reaction is completed in a 3-liter tank at 100 Kelvin. It's initiated with 3 moles of the COCl2. At equilibrium, which one or more of the following represents the moles of each substance that could be present? Could be present. All right, so there's a couple things we have to think about. If we know the initial amount of our COCl2, we have to remember stoichiometrically, the change line is going to be all the same number because it's 1 to 1 to 1. So if we thought, let's say 1 mole of everything reacted, the change line is 1 mole. Well, if the change line is 1 mole, then option D would have to be correct because you would do 3 minus 1 and get 2, 0 plus 1 is 1, 0 plus 1 is 1. So that's why D works. The key here is the stoichiometry follows the change line and it's 1 to 1 to 1. B could also work because the change line could be 2. And you would say 3 minus 2 is 1, 0 plus 2 is 1, 0 plus 2 is 2, and 0 plus 2 is 2. The other options can't work because when you're trying to fill in the ice diagram, it's not possible to have 2 all at the end because your change lines all have to be the same. So this definitely takes a little thought process, but it has to do with the stoichiometry, the change line, and the 1 to 1 to 1 relationship. All right, number 33. This question has us trying to manipulate the reactions to get the K for a third reaction. So the worksheet would be properties of the equilibrium constant, which I think is 7.6. I think it's the topic 7.6. So reaction 1, reaction 2, all that we have to do here is add these 2 reactions to get the third reaction. We don't have to do any manipulating. So this one's pretty straightforward. But remember, when you add the reactions, you're going to be multiplying the values for K. So if you had to do any other manipulation, we want to remind ourselves here, if you reverse the reaction, you take the inverse of the K. When you add the reactions, you multiply the Ks. In this reaction, you're just adding the 2. So you don't need to worry about any of those other rules, but I wanted to remind you of them. Remember, this could also be done with KP. This can also be done with KSP as well. All right, 34 is just a little kind of like a particle representation. It was a way for us to try to have you think about what would be the equilibrium, determine if the equilibrium constant will be greater than or less than 1. So you really just have to consider your products and your reactants. So we have our product here, which is NH3, which is our triangle. So we're going to have 1, 2, 3, 4 products. That 4 is going to be squared because of our 2 here. And then we have all of our reactants down here. When we think about that and we put that all together and we solve for our K, we're going to end up with a value that is going to be less than 1 when we think about our ratio of our products and our reactants. 35 is just a little bit about the equilibrium constant. What do you know is true about the equilibrium constant? Again, the equilibrium constant doesn't have any units, which is why A cannot be true. It doesn't change if concentration changes, but it is temperature dependent. That's the key idea there. All right, we're rounding out the last couple. Chemical reaction here for number 36, we have the Kp, which is much greater than 1, which tells us our products are favored. That's the only thing we really can get from that. Number 37, this is another kind of situation like that last one where we were looking at what's possible to have at equilibrium. The key here is the equilibrium constant is 3. So you have to think about, because these are in a 1-to-1 ratio, products over reactants has to equal 3. So what possible combination of y over x gives you 3? So you can see 0 over 12, no. 3 over 9, no. 9 over 3, that's where we're going to get our 3. Now this one can't be possible because you can't make more product than your original amount of reactant. That's why that's not a choice. Even though it does equal 3, how can you start with 12x and end up with 36y? It's just not going to happen. We've got some KSP problems here. Which or one or more of the following would decrease the solubility of calcium fluoride? Now, when you see decrease the solubility of calcium fluoride, it means cause a shift to the side where calcium fluoride is a solid. Because if it's a solid, it's not in the solution, therefore the solubility has gone down. So that's what we're looking for. Which shifts cause a shift to the reactant side? So, yes, we heat it up. Heating it up is going to shift to the reactant side. Pressure is not going to cause any changes here. Dissolving the calcium fluoride in a solution of sodium fluoride instead of pure water. This is another important property of solutions. If you were trying to dissolve some ionic substance in pure water, then you tried to dissolve the same ionic substance in something that already contains one of those ions, that number of ions is going to be smaller because you're essentially trying to dissolve it in something that already contains the ions that you're trying to get into solution. So just remember, anytime you're trying to dissolve something in water, you're going to get a certain amount of solubility. If you try to dissolve something in a solution that already contains one of the ions that you're trying to dissolve, the solubility is going to be less. That's why C is going to work. Adding calcium nitrate to a saturated solution. Well, if you add calcium nitrate, that's like adding more calcium, which again is going to shift to this side, which is the solid side, which means the solubility goes down. Another special note, you can already see here that the solubility of calcium fluoride is already pretty small from the KSP value. As calcium fluoride dissolves in water, exothermic reaction, temperature of the water will go up. All right, last one before we get to the open response. Crystals of sodium carbonate are added to the saturated solution of calcium fluoride. Now here's that point where I'm telling you that calcium carbonate is insoluble. That's that clue I was mentioning earlier when we were talking about, I forget which question it was. I said, oh, the clue might be, I'm going to give you the KSP. And here it is. So the KSP is really, really small. So if we end up precipitating some of the calcium carbonate, let's see what's going to happen. Let's go back. Some of the calcium here, calcium carbonate, yeah, some of the calcium here is going to react with the carbonate and it's going to get removed. So we're going to remove some of our calcium because it forms a precipitate. Now, as we remove some of our product, the reaction shifts to make more of the calcium ions. So that means some of this solid is going to dissolve. All right, so that's what's going to happen. The precipitate of calcium carbonate would form, that's first, removing the calcium ions, shifting the equilibrium right, and also dissolving some of that calcium fluoride. Now, in this whole shift that's happened, we end up with a different concentration of fluoride ions. What would be now the concentration of calcium ions? Well, the big idea to remember, excuse me, is that the value of KSP doesn't change. So if the KSP is exactly the same, but now you know what the concentration of the fluoride ions is, you can calculate the concentration of the calcium ions. The concentrations of these two ions here have to be in an inverse relationship with one another if they equal a constant. Think about this from a pure mathematical standpoint. P times V equals constant. These two ions multiplied together equal a constant. So if one of your ion concentrations all of a sudden goes up, the other ion concentration needs to go down to keep equaling that mathematical constant. So you could also get a question like this conceptually. If one goes up, the other one has to go down so that they can keep equaling that constant. All right, I'm going to stop here, and I'm going to do the open response screencast separately. Hope this helped. Make sure you email your teacher if you have any questions.